An interesting thing that can happen and occur with these carbocations for all of these unimolecular reactions is that we can get a rearrangement of carbon skeletons to form a more stable carbocation. Right, so it's going to be something that we have to look out for. So carbocations can rearrange their skeletons to form more stable ions. Now, ionization of unstable primary carbocations can be forced by using silver nitrate, or by increasing temperature, or by doing both. And there are two types of rearrangements that we're going to see. The first one is called a hydride shift. So let's go through and write this out. Just imagine here that we have this molecule, put an iodo group here, right? And then what we're going to do is we're going to put an H off of this carbon here. And we'll put an H off of this atom. And then we're going to come over here with our other carbon, and that's going to be an H, and then a CH3, and then another CH3. Now, this is a primary alkyl halide. So it's the first thing to note here. And then let's look at our reaction conditions. So let's go through and let's put in here, how about like H2O, and then let's put in AgNO3, and then remember that little triangle means we'll heat it up. Now, first step, as we have seen before in an SN1 reaction, is we are going to boot off that leaving group. So what this is going to form is our carbon here with an H, another H, and then a carbon with an H, a CH3, and a CH3. And that'll be a plus charge right there. And then also I want to show you here we make I minus. Now notice that this is a reversible reaction. So I wanted to show you, how does silver nitrate come into play here? Well, there's another reaction that's happening here too. So silver nitrate dissolves into silver ions and nitrate. So silver, when it comes around and it sees iodide, it goes through and it forms silver iodide is a PPT. It crashes out of solution, and this pulls the equilibrium over to forming the carbocation, right? Because through Le Chatelier's, you're reducing this concentration. Le Chatelier's wants to make more of it. Now, we also notice here too that, look, we have a primary carbocation. So this carbon with a plus charge here, that's a primary carbocation. So then what happens is we're going to take one of these H's. We're going to take this H right here. And that H is going to end up moving over to the carbon with a positive charge. So we're going to take this H right here, and it's going to take its set of electrons along with it, and it's going to jump over here just like so and come to this position. So this is often a little confusing to students at times. So we're going to come this direction. Let's write it out, right? And let's see what happens. So we're going to just simply take that H and we're going to stick it on that carbon. So we'll have 1, 2, 3 carbons on this position. And then over here, we'll be left with a CH3 and then another CH3. But look, the plus charge is going to go here. So in effect, you've gone from a primary carbocation over here to a tertiary carbocation. So that's a favorable thing. So we often see a shift that looks like this. For predictive purposes, let's assume that the shift occurs and that the more stable carbocation is the one that predominantly reacts. So that's our hydride shift. Now, what about an alkyl shift? Well, alkyl shifts are just kind of permutations of what we just saw. So let's take a look at what an alkyl shift looks like. So we'll have an H carbon iota group, and then over on this other carbon, I want to put on here a CH3, and then another CH3, and another CH3. So we'll put a total of 3 on that carbon. So that carbon right here is going to have 3 CH3s on there. And the first step of this reaction is similar to what we saw above. It's the first step of all SN1s. So we're going to kick off iodide. And again, this is going to be a primary carbocation. So what we might use here is silver nitrate, a little bit of heat, right, and water to carry out the rest of the reaction. We're just looking at the formation of the carbocation. All right, so then what are we going to get? Let's take a look. We're going to get our carbon. That's going to have 2 H's on it. And then our other carbon has 3 CH3s. That's not going to change at all. And that's going to leave us with a plus charge right where that carbon is. So the same deal, we have a plus charge right here. And again, just to point out here, we have a primary carbocation, right? So now neighboring to what we're looking at here, we have only methyls or only carbons. So in this case, we're going to take a set of electrons and we're going to move over and we're going to jump over to this position right there. So that will give us here our H, now with a CH3 and an H there. So that's the CH3 that jumped over. And then this carbon is going to have 2 CH3s, and that'll give you a plus charge right there. Now that's a tertiary. So you're going from a primary again over here to a tertiary carbocation. So a favorable shift as far as this is concerned. Now you may wonder, why didn't the last reaction have a methyl shift? Well, let's look at it. So let's come back up here and just maybe right down below here, I'll go through and let's take a look. What would happen if we did a methyl shift with that? So I'm going to start off with this guy, with our H's, because that's our intermediate. We know that the iota group will be lost. So here's an H, CH3, and a CH3. Well, if we did a methyl shift here, we'd come over here and we would do this, right? That would give us an H with a carbon, right? An H, and then that's the newly kind of moved over alkyl, in this case the methyl. And then over here we'd have a carbon with an H and a CH3. So we would have a plus charge right here. So that takes you from a primary to a secondary. And that's not as good as going from a primary to a tertiary. So we don't see this type of shift readily occurring. So if there's an H that's neighboring, that's the one that we typically move over before we start pulling over any alkyl groups. Again, because you're going from a primary here to a secondary. That's favorable, but not as favorable as going to a tertiary carbocation like this. Now the other thing that can occur here too, guys, is that this can happen in rings. And it usually just kind of blows students' minds. So let's take a look at this and just do a little example. Let's look at this as an example. So we'll come up here and we'll put an iota group here. So step number 1 with this would be kicking off our leaving group. So I'm going to write out carbons here. Carbon, 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 and now that's a CH2 with a plus. That's an H, H2, H2, and H2. And of course we need like silver nitrate, heat or something in there to promote that ionization. So here we have a primary carbocation. So what probably happens here is that one of these bonds comes over and swings around and makes a bond to this. So two problems with this: primary carbocation, and also we have cyclobutane, which has sufficient ring strain in it, right? So if we could get this to a 5-carbon, then that might be a favorable thing to happen. So let's do this. So when we do this movement, what we're doing is basically erasing this bond. And then we're going to make a new bond right there, right? So sometimes students like to just use like a little side note or a scratch paper or something, and you can write it out like this. So here's a CH2, here's a CH2, CH2, that's a CH, this is a CH2 that's right there, right? And remember what's happened here, and I'll kind of write this out, is that bond right there is disappearing. So we say goodbye to that bond, and then we're making a bond right there, right? So that's our new bond. And now when we look at the structure, we can all see that there must be a plus charge right there because you have an incomplete octet. And then we wouldn't leave it like this. This is pretty ugly looking. So we count it up, 5 carbons. Now we clean up the structure. So when we clean this thing up, we go back to our bond line structures, and then that would be your structure. And then this thing would further react right via SN1, essentially. And as we'll see shortly, there can be another accompanying reaction with this, which is an E1 reaction. So for rings, what we're doing is we're kind of trying to go to a 5-carbon ring. If we can do that, that's a good thing. Or like a 6-carbon ring. And that's usually from like a 3 or 4 carbon. So that's the type of shift that we're looking for. So that's for rings. And then for these alkyl or hydride shifts, we're looking for mostly primary to tertiary. Those are the big ones that we'll keep an eye out for.